Have you ever held a piece of gold? Felt its surprising weight in your hand? It's more than just a shiny, pretty metal. It's a relic from the most violent events in the universe. So, why is gold so rare? And what makes it so chemically perfect for everything from jewelry to spacecraft? Let's dive into the incredible science of gold. To understand gold, we have to go back in time, way back before the Earth even existed. At the very beginning of the universe, the Big Bang created the lightest elements, hydrogen and helium with a little lithium thrown in. Every other element on the periodic table, including the iron in your blood and the oxygen you breathe, was forged inside the fiery hearts of stars through nuclear fusion. Stars are cosmic factories, smashing lighter elements together to create heavier ones. They can make carbon, oxygen, all the way up to iron. But there's a problem. Creating elements heavier than iron through fusion doesn't release energy, it consumes it. So, a regular star, even a massive one, can't make gold. For that, you need something far more spectacular. For a long time, scientists thought supernova, the explosive deaths of massive stars, were the primary source of heavy elements like gold. When a giant star runs out of fuel, its core collapses, and the outer layers are blasted into space in a cataclysmic explosion. The intense energy and flood of neutrons were thought to be perfect for creating the heaviest elements. And it's true, supernovae do create some gold. But recent discoveries have pointed to an even more extreme and violent cosmic event as the main gold factory in the universe, the collision of two neutron stars. Imagine two city-sized objects, each more massive than our sun, crushed down to unimaginable density. These are neutron stars, the collapsed cores of dead giants. When two of these cosmic titans spiral into each other and merge, the resulting explosion, called a kilonova, is one of the most powerful events in the universe. This collision unleashes a tidal wave of neutrons and energy so immense that it can rapidly forge huge quantities of the heaviest elements, including gold, platinum, and uranium. In 2017, astronomers directly observed gravitational waves and light from a neutron star merger. When they analyzed the light, they found the distinct signature of freshly created gold. Hundreds of Earth masses worth of it, all produced in a single event. So the gold in your ring isn't just stardust. It's the fallout from a cosmic demolition derby of epic proportions. This cosmic origin story is precisely why gold is so incredibly rare. It requires such specific, violent, and infrequent events to be created. Then, these newly formed elements have to get swept up in the cloud of gas and dust that eventually formed our solar system and our planet about 4.5 billion years ago. When the Earth was young and molten, its heavy elements, like iron and gold, sank towards the center, forming the core. This means most of the Earth's original gold is locked away thousands of miles beneath our feet, completely inaccessible. The gold we can actually mine today is thought to have arrived later, delivered to the Earth's crust by asteroid impacts during a period called the Late Heavy Bombardment, billions of years ago. So the gold we have is the result of a double lottery, created in a rare cosmic explosion and then delivered to the surface by celestial bombardment. It's estimated that if you gathered all the gold ever mined in human history, it would form a cube only about 22 meters on each side. That's it. That's all we have. But its rarity is only half the story. What makes gold so special is its unique set of properties, which all come down to its atomic structure. Gold is element number 79, meaning it has 79 protons and, in its stable form, 79 electrons. These electrons are arranged in shells or orbitals around the nucleus. Now here's where things get interesting, thanks to Albert Einstein's theory of relativity. For heavy elements like gold, the inner electrons are pulled so tightly by the 79 protons in the nucleus that they have to move at speeds approaching the speed of light. This relativistic effect causes them to become heavier and shrink their orbits. This, in turn, affects the outer electrons, making them more tightly bound to the atom. This relativistic effect is responsible for gold's famous color. Most metals are silvery white because their electrons can absorb and re-emit photons from all parts of the visible spectrum. But in gold, the relativistic contraction of the electron orbitals changes the energy gaps between them. This makes the atom absorb blue and green light while reflecting yellow and red light. So, when you look at gold, the beautiful warm glow you see is a direct consequence of Einstein's theory of relativity in action. Without it, gold would look just like silver. Beyond its color, gold's electron structure makes it incredibly unreactive, or noble. Its outermost electron is held surprisingly tightly, meaning gold doesn't like to share or steal electrons from other elements. This is why gold doesn't rust, tarnish, or corrode. You can leave a gold coin at the bottom of the ocean for 1,000 years, and it will come out looking just as shiny as the day it was lost. This chemical stability is why it's been a symbol of eternity and purity for millennia, and why it's the perfect material for jewelry that lasts a lifetime. It won't react with your skin, the air, or water. It just stays gold. This same unreactivity, combined with its other properties, makes gold indispensable in modern technology. Gold is an excellent conductor of electricity. Since it doesn't corrode, it guarantees a reliable, long-lasting connection. That's why you'll find a thin layer of gold plating on the critical connectors in your smartphone, your computer, and in high-end audio and video cables. It ensures the signals pass through without any degradation over time. Even the most advanced pieces of technology, like the James Webb Space Telescope, rely on gold. Its giant mirrors are coated with an ultra-thin layer of gold because it is exceptionally good at reflecting infrared light, which is the light from the most distant galaxies that the telescope is designed to see. Without gold, we couldn't peer back to the dawn of the universe. Furthermore, gold is incredibly ductile and malleable. This means you can draw it out into a wire or hammer it into incredibly thin sheets without it breaking. In fact, a single ounce of gold can be stretched into a wire 50 miles long or beaten into a translucent sheet of gold leaf that's only a few atoms thick. This allows us to use tiny amounts of it very efficiently, whether for decorating a picture frame or coating a satellite to protect it from solar radiation. So when you think about gold, don't just see a shiny metal. See the aftermath of colliding neutron stars. See the physics of relativity painting it yellow. See the stable atomic structure that makes it an eternal symbol of value and a crucial component in our most advanced technology. It's a journey from the most violent corners of the cosmos to the most delicate electronics in your hand. A substance born from cosmic fire, delivered by asteroids, and perfected by the laws of physics. Thank you so much for watching and exploring the incredible science of gold with me. If you found this as fascinating as I do, please hit that like button and consider subscribing for more journeys into the wonders of our universe. Let me know in the comments what other elements or scientific topics you'd like to see covered next. See you in the next video.